This is Algebra 2 with Trig, 6A.2. We'll be talking about exponential growth and decay functions. When we talk about exponential growth, we typically have an equation that's going to be 1 plus r to the t value. Another way that we have seen exponential growth is y equals a b to the x power. Essentially, our x is being represented by t, our a is being represented by p, and this is our exponential growth. Here, when we talk about buffalo, there's 38 buffalo. That's going to be our population. That's going to be the initial amount that we have. So we're looking for the amount if we start at 38 buffalo, and it's going to grow by 7%. We're going to increase. So this is 1 plus your rate. By how much is it changing? It's changing by 7%. This b value doesn't quite do it justice. So the b value is really what we have going on here with the 1 plus r. So if we're increasing by 7%, we're going to call this 1 plus 0.07 because that's 1 plus 7%. You don't want to just put down 0.7%. You don't want to know what 7% of 38 is. You want to know what 100% and 7% more. You want to know what the total is if you add 7% to the 38. And we want to know after t years. So we're trying to write a model. We're not answering a question. We're just writing a formula or writing a model. So it says n, so it probably wouldn't be the letter A. It would be n equals 38, 1.07 to the t power. That would be our n buffalo. So how many buffalo are we going to have after 7 years? So 38 buffalo, 1.07, that's increasing by 7% after 7 years. So we use a 7 for the t value. So we have 38, 1.07 raised to the 7. We get 61.01. You could think about rounding it, so 0.02 if you wanted to, but it's about 61 buffalo. Because you're not going to have a decimal version of a buffalo. So using our graphing calculator, we can find out at what year would we have 53 buffalo. So we're going to make a graph out of this, but let's go to our graphing calculator. It says that we would use that. I would suggest to do second plus 7 to reset, 1, 2, so we're all at the same spot. We don't have to worry about our windows or what we've typed in. It all clears it out. So we're putting in 38, 1.07 raised to the t, which is x in our situation, because that's what our graphing calculator uses. We want to find out when is there going to be 53 buffalo. So we're going to put that down as a separate line. So we're expecting our graph to be exponential growth. And we want to know when is that exponential growth going to be 53. Our equation is 38, 1.07 to the x power. So this is what we're trying to figure out, is what is the x value when our exponential growth hits 53. So we have to go to Window to be sure that our graph is going to show a y value that is up in the 50s. So I'd actually pick a number considerably larger, so you're sure that if you just pick 55, then 53 is going to be just below that. And if you pick 60, it's just going to be down a little bit. So 65, 70 will give you plenty of room to get your graph in there. So you see where the exponential growth is coming in, and then you're 53, and we want to find out where that x value is that would touch this location. We would do that not by using trace and arrowing over, because that's not going to be very accurate. We want to use second trace. We want to calculate for the intersection. So you have two equations that you've typed into your calculator. You have your first curve and your second curve. Your first curve, is this the curve you're thinking of? Of course it is, because it's only one of the two that you have. Is that the other equation? Of course it is, because you only have two of them. Hit enter. Now it says guess. Guess is important if it crosses twice, but since it only crosses once, you can get away with hitting enter right now. Or if you just want to be sure, get closer. It doesn't matter. Get closer and hit enter. So you'll see that we get 53 when the x value is 4.92 if we round. Only round your final answer, so 4.92. So those would be years. And we want to be as accurate as we can. Don't round that up to 5. If you want to say about 5, that's fine. But you should show your 4.92. Show your real answer. And then go ahead and do your approximated stuff if you feel that that's necessary. So that's how we do a growth model. Now, when we talk about money, we have a few other variables that come into play. We have compound interest. And that's 1 plus r over n, nt. So your interest rate is going to be broken up into smaller amounts, and you're going to receive parts of that interest at different times throughout the year. That's called compound interest. The P is your initial amount that you're investing. N is the number of compounding periods. Are you going to get, like down here, we're going to do it monthly, so our N is going to be 12. You could do it bi-monthly, you could do it daily, you could, lots of different ways, weekly, whatever you want. So interest rate, our interest rate as a decimal. That's the key part. A lot of people make a mistake here and they only use 7 because they think that they're, or in this case 3.5, because they're doing interest rate not as a decimal. That would need to be 0.035. So annual interest rate. Annual means we're only going to get it once a year. So really you can get away with P1 plus RT because your denominator is going to be a 1. Your N value is a 1. You're getting a compound annually, once a year. So you don't really need the N at all. You can put the N there if you want. You're putting in $2,900, 1 plus 0.035, because it's 3.5%. You got to move the decimal spot 2 to the left, 0.035. And we're doing this for 3 years. 2,900, so this is 1.035 to the third power. That 1.35 is what's being repeated 3 different times. So 2,900, 1.035 to the third power. $32.15 and 28 cents. The third digit's a 1, so we don't round any values. So that's if we get our interest once a year. Now we're going to look at monthly. What if we compound this monthly? That means we're going to use P, 1 plus R over N, NT. So we're still looking at the 2,900. Still have an interest rate of 0.035. Now we're going to divide that 0.035 by 12 different months. That means we are going to get a fraction or a portion of our 3.5% each month. We're going to get a 1/12 of it every month. And then we're going to do a calculation, and we're going to end up doing 36 calculations over the 3 years. So you can type, now since you've written this out, you can calculate this out, but then we're just rounding numbers. Okay, I'm trying to have you not round your work. You can round your answer, but don't round your work. So it can be safest as long as you write out what your initial equation is here. That's your work. 2,900 times, I use parentheses, 1 plus, now I have a fraction, I have to use parentheses again just to be sure I keep things organized, 0.035 divided by 12. Okay, there's my fraction. Close off my parenthesis, that's going to be raised to the 12 times 3. You can just type in 36 or call it 12 times 3. And that'll give you your $3,220.57, because that would round up, 57 cents. Now, if you use a rounded value, I've done this calculation before, and I used a rounded value. If you come in here, you calculate this out, and you'll see you'll get 0.0029. If you do that 1.035, let's see, 0.035 divided by 12, you get 0.0029, 16667. So if you round that to the 1.029, or even worse, 0.003, you'll get a different result, different answer. You want to keep it as accurate as you can. All right, in this situation, we want to have $2,500 in the savings account after 5 years. Find the amount that you deposit. What are you going to start with? A equals P, 1 plus R over N, NT. What are we going to start with if we have 4% with an interest rate that's compounded daily? What's daily mean? So we want $2,500 in our account. We don't know what we're starting with. 1 plus, our interest rate is 4%, so 0.04. Daily. How many days are there in a year? 365. So 365 times 5 years. There's your equation that you need to write out. Well, where's this number come from? So now we can calculate this out. You can do it all in one step, but I want to discuss about rounding work. It does make a difference. So 2,500 equals P. We can type this portion into your calculator. So 1, well, we should use parentheses, 1 plus, and we want the 0.04 divided by 365 to be the fraction that we're adding to the 1. But we close that parenthesis off, and now we raise it to the power of 365 times 5. We could write down all the details. We could figure out what this is and add it to the 1 and figure out what that is. We really don't need to, as long as we're being honest with ourselves. 1.221, that would round to a 4. 1.2214. Just writing a lot of numbers. It doesn't matter what you round here. If you want to call it 1.2 or 1.22, that's fine, because you're not going to divide by that number. You might write that number, because it's kind of silly when some of you write so many values after the decimal, because you're trying to be as accurate as you can. But the accuracy comes with your calculator. So we're going to take the 2500 and we're going to divide. Don't put down 1.2214. Put down second and the ANS button, the answer, the previous answer needs to go in that spot. That'll use the real value that you calculated up here and divide it into 2500. So we have $2,046.85. Now notice what I did on another situation where I did round, and look what I did. I rounded 1.22, and when I did that, I got 49. 2,049. We came up with 2,046 because we used the real value, not a rounded value. Yes, I wrote a rounded value, but I calculated with the real value, the previous real value. So we flip over. Now we'll talk about decay. Exponential decay. We have the amount that we start with. We have 100% of that amount, but we're going to decrease. So we're using subtraction, not plus. We're subtracting some sort of rate that will lose, that will depreciate over time, to a power saying that we're going to repeat that for typically every year, whatever the storyline is. So a new flat screen TV is $1,200. The value of the television decreases by 21% each year. That's probably pretty accurate. Write an exponential decay model giving the television's value, which is going to be called Y, after T years. So we'll say Y equals the initial amount, that's the P, is 1,200. 1 minus, you're losing 21%, so 0.12 after T years. So what does that mean? That means you're only going to have 79% of your value of the previous year, 0.79. 1 minus 2,1. So if we want to know how much the TV is going to be worth after 2 years, that's 1,200, 0.79, and we get 79% of the previous for 2 years. So we got 1,200, 0.79 squared. And that's going to give us a value of $748.92. A used TV is cheaper than a new TV. Using your graphing calculator, graph the model and estimate the value of the television. When will it be $300? So we're going to graph. We're going to take our equation and we're going to find out when will this equation be $300. Notice that this is exponential decay. It's falling. It's less than 1. So your graph should be decreasing over time, and we want to figure out when is that going to be 300. Our equation that we'll be graphing is 1200.79 to the x power. That's what we should be working on. And I probably have estimated this pretty poorly. It should, if it's actually reality, it should cross above that. It's not going to cross in negative years. It's definitely going to cross after positive years. So let's find out what this is going to be. Again, I would suggest second plus 712. That'll clear your calculator, so when you go into y equals, you're not dealing with things in your way. We have 1200.79 to the x power. We want to know when this is going to be 300. You could look at your table, but that's just going to give you an approximation. That's going to give you concrete x values, and we might have a decimal x value. So we would need to see our graph when it's up at 300. So I need my window to be larger, my y value maximum to be larger than 300. Let's say 400. So when this comes down, you see it's depreciating, it's falling to the right. There's my 300 mark, and this is the spot I'm looking for. So second trace comes down to intersect, number 5. Are these your two equations? That's my first one. That's my second equation. I hit enter. Now it wants you to guess. So you just get close to your answer. It really doesn't matter how close you get. Hit enter. And it tells you 5.88, and these would be years. And 5.88, not dollars, these are years. All right, last two here. Let's talk about these. These get a little confusing. Here we don't have a graph. We don't have to write equations. We're given our equation. In an exponential growth model, identify the initial amount. What is our initial amount in this equation? It would be 6. It's the value in front. It's the leading coefficient. So it's 6. The growth factor. What are we multiplying again and again and again and again? That's the 1.017. That's the growth factor. What is the percent increased?
1.7.
You would need to move the decimal over 2. So that would be 1.7%. That is your percent of increase. Your growth factor is 1.017, but your percent of increase is the amount that's above the 1 as a decimal. Oh, really as a percent, which happens to be a decimal in this case. Okay, exponential decay. Our initial amount is the amount in front. The decay factor. How much, what's the value that's being multiplied again and again? 0.62. What is the percent that you're decreasing? This gets a little confusing for people. All right. You have 100% and you're minusing some rate. And when we do that, we're getting the 0.62. So we need to minus the 1 across, and that gives us a negative 0.38. And you divide by your negative, and that'll give you 0.38. So there must be a 38%, so move the decimal spot over 2, 38% decrease to give us this equation. That's the amount that it takes to get to 1. If you just want to think about it like that. What does it take to get up to 1? That's the amount that is being subtracted from 1 to give us your 0.62. Good job, everybody.